Um, First, let's go ahead and look at this problem here. It says find any intercepts and test for symmetry with respect to both axis and the origin. So they give us here an equation, which is y equals minus 2x plus 1. And we first need to find our x-intercepts. So again, just to review, to find our x-intercepts, what we need to do is we need to set y equal to 0 and then just solve for the x. So again, we're going to replace the y with a 0 and go ahead and solve for x. So the first thing we do is subtract 1 on both sides, and then we're going to divide by a negative 2 on both sides, and we see that x is equal to 1/2. Again, this is the equation format of the x-intercept to plot it here on our page is asking us to write it as an ordered pair. So then again, my x value for my ordered pair is 1/2, and the y value here was 0. Okay. Now to find the y-intercept, I need to set x equal to 0, then solve for y. So let's go ahead and do that. So we will have y equals minus 2 times 0 plus 1. Again, minus 2 times a negative 2 times 0 is 0. 0 plus 1 is 1. So our y-intercept in equation format is y equals 1. And as an ordered pair, again, x equals 0, comma 1. Yes, and then these are the parentheses to show the ordered pair. So now let's check for symmetry. So to check for symmetry, okay, if we were to graph this graph, okay, it doesn't have any asymmetry, just because if we test it on the x-axis and y-axis, the way I like to tell my students about symmetry is if the graph is reflected on either of the axes, and we don't on here. So again, on this particular one, we'll have no symmetry. So the way algebraically to check for symmetry without graphing is we change the sign of the y value, okay? And then if we get the same equation, then it has that axis symmetry. So again, an example, I have this equation y equals minus 2x plus 1. And what I'll do is I'm going to change the y value sign to a negative 1. And if I solve for y again, I end up getting y equals to 2x minus 1, which is not the original equation. So again, it does not have x-intercept. Similarly, to check for the y symmetry, I changed the sign of the x value and then solve for y again. And if this gives me the original equation, then it has y-axis symmetry. So again, I have this equation, and I'm going to change the sign of the x value, and the new equation is y equals 2x plus 1. Again, it's not the original equation, so hence it does not have y-axis symmetry. And to check for algebraically for the origin symmetry, I would change the sign both of the x and the y. And again, solve for y. And if I get the original equation, then it has origin symmetry. So here I would have minus y is equal to minus 2 times the negative x plus 1. Again, a negative with a negative is a positive 2x plus 1 multiplied by a negative on both sides, and I get y equals minus 2x minus 1, which is not the original equation. So hence this equation, and just for you guys to get ready for your final, um, linear equations will not have any symmetry, okay? So um, let's look at this now. New example. It says write the standard form of the equation of the circle with the given characteristics. Okay, so first we need to know what the standard form of a circle is. Again, the standard form of a circle is given by x minus h squared plus y minus k squared is equal to r squared. Again, where my center is hk and r refers to my radius. So in this particular problem, they gave me the center, which is negative 4, 2. So this applies to the h and k. H is negative 4, k is 2, and then my radius is 2. So all I have to do to get the standard form of the circle is just plug in these variables or these numbers to these variables and simplify. Okay, so here I have x minus a minus 4 squared plus y minus 2 squared is equal to 2 squared. So again, in the first one, a negative with a negative is a positive. So I will have y plus 4 squared. Again, I didn't have to simplify anything for this for the k value, and 2 squared is 4. And voila, would be the answer. The equation with these given characteristics in standard form of a circle is given by x plus 4 squared plus y minus 2 squared equals 4. Okay. All right, let's look at this next example. Write equations of the lines through the given point that are parallel and perpendicular to this line. Okay, so the first thing that we need to do and know is we need to know the slope of the line that we wanted to be parallel and perpendicular. So for parallel, for two lines to be parallel, they have to have the same slope, but but different y-intercepts. For two lines to be perpendicular, I like to say that they have a opposite slope, and I'll go over that right now. So let's go ahead and start. So if I need to find an equation that is parallel to this line given 8x minus 2y equals 3, I need to know its slope. And the best way to find its slope is just to convert it into slope-intercept form. And that means solving for y, or isolating y. So if I get 8x minus 2y equals to 3 and solve for y, I end up that y is equal to negative 3 halves plus 4x. So here, the slope is 4, okay? So again, on the intercept, I'm not interested in the intercept. This one has a negative 3 half as the y-intercept where it's crossing the y-axis, but I don't need that. All I need is the slope. Okay, so let's go ahead and find first the parallel equation. A parallel equation to this line will have the same slope of 4, but they gave me some more details. They want me to have this line go through this point, 8, 1. So what I'm going to do is I'm going to use the point slope formula to find my equation. So the slope point formula is given by y minus y1 is equal to m times x minus x1, where x1 and y1 is the point that I want to go through, and m is the slope. Okay, so let's go ahead and plug in these values to my equation. So we have y minus 1 is equal to 4 times x minus 8. The first thing that I need to do is let me put this equation in slope-intercept form. That's how your computer, or whether you're taking a test on paper, they want you to answer the equation in slope-intercept form. So first we're going to distribute that 4 into the binomial x minus 8. So we have 4x minus 32. Then the next thing that I'm going to do is I'm going to subtract 1 on both sides. And when I do that, I'm going to get y is equal to 4x minus 31. And if you see here, this equation has the same slope as before, has a slope of 4, and it has a different y-intercept. Again, the one before, or the one that was given, had a fraction for the slope, and this one, the y-intercept is negative 31. So now this line is parallel to this line, and it passes through this point. So let's do the second part, the perpendicular. But for the perpendicular, I need to use the perpendicular slope. So the way I like to tell my students is the opposite slope. So for instance, the parallel had a positive slope, so then the perpendicular has to have a negative slope. And then I have 4. I convert 4 into a fraction, 4 over 1. The opposite of the fraction is its reciprocal. The numerator becomes the denominator becomes the numerator, so that gives me 1/4. So this value here, this slope, negative 1/4, is a perpendicular slope. That's going to allow me to have the line perpendicular to the one given. But again, it still needs to go through the same point, 8, 1. I'm going to use my slope-intercept form equation once again. So let's go ahead and plug in what I have. I have y minus 1 is equal to minus 1/4 x minus 8. Again, I'm going to distribute the negative 1/4 and simplify. Then I'm going to add 1 on both sides. And when I do that, I get y is equal to a negative 1/4 x plus 3. And this would be my answer. This equation is perpendicular to the equation given, or to the line given, that goes through the point 8, 1. Okay. All right, let's look at some more examples here. On these particular ones, we have two functions, and what they want us to do is just do basic math operations with these two functions. So the first one is read f plus g of x, and what they want me to do is basically just add function f with function g. So what I like to do is I like to rewrite this so I can just do a substitution method per se. So here, what they really want me to do with f plus g of x is just do the function f of x plus g of x. So again, I color coded them so you can see them. F of x is in red, which is 9x plus 1. G of x is in blue, the x squared minus 1. And I add these two equations together. So to simplify, I just need to combine like terms. So I only have one x squared term, so that stays alone. I only have one x term, so that which is 9x. That does nothing happens, but I have two constant terms. I have a +1 with a -4, so that gives me a -3. Okay, so very similar to B. B, they want me to do f minus g of x. So I like to rewrite this. What they really want me to do is just do f of x minus g of x. So again, function f of x is in red, g of x is in blue, and I'm going to subtract these two functions. But before I can combine my like terms, I need to distribute this symbol here, the negative or the subtraction. There's basically a -1 here in front of this binomial. So when I multiply -1 times x squared, that gives me -x squared. A -1 times a -4, that gives me a +4. Now I can combine like terms. I only have a x squared term, so that stays alone, -x squared. I only have one x term, the 9x, that stays unaltered, but I do have two constant terms. +1 plus 4 is going to give me the +5. Okay. Now C, they want me to multiply two functions together. When I have two letters together, what that means is I'm multiplying, right? So this is read f of g of x, right? So basically what they want me to do is multiply f of x with g of x. Again, f of x is in red, g of x is in blue. And for this one, I have to distribute both terms, or in other words, FOIL. 9x times the x squared is going to give me 9x cubed. 9x times a -4 is going to give me a negative 36x, excuse me. 1 times x squared is x squared, and a +1 times a -4 is a -4. Then I would combine like terms, but in this particular case, all four terms that I have here are distinct. None of them are like terms or the same terms. So then I would just have that answer. And again, if you put this on the computer, it will accept it this way, but we like to put it in a descending order. This is our general form, right? But you don't have to. All right, and then the last one is f divided by g of x. And what they basically want me to do is just divide function f of x with g of x. So again, f of x is in red, 9x plus 1, g of x is in blue, the x squared minus 1. There's nothing that I can factor, there's nothing that can simplify, there's nothing that can cancel. So then my answer is just that, 9x plus 1 over x squared minus 4. Now also, on your homework, and you may be asked on your test, is to find the domain of this division. Okay, and the reason why they only ask you about the division one is because this is one of our functions that has a restriction, right? We never want to zero on the denominator. So let's go ahead and calculate that. So if you don't see it, we set the denominator equal to 0, x squared minus 4 equals 0, and then we solve. And again, using our 0 or a square root property, I'm going to add 4 on both sides, take the square root of both sides, and I get that x is equal to plus or minus 2. So then my domain in interval notation is from -infinity to -2 parentheses. Again, the infinity symbols will always have a parenthesis, okay? The parentheses means that it's not a number, or I don't want to include that number, okay? So infinity is not a number. It's a number that keeps on going, never stops. And I don't want to use a -2 or a +2, because if not, I would get an error, okay? So then we have this symbol, the U, meaning and or union, -2 to 2, union 2 to infinity. Okay, and this is my answer that you need to give for your test in interval notation. All right. So let's review inverse functions. Okay, so let's review just really quick what a function is graphically. Whenever they give us a graph, to find out if the graph is a function, what we do is we perform the vertical line test, right? If our imaginary vertical line crosses our graph only once, then that means the graph is a function. So in this particular one, if I do an imaginary vertical line, okay, or I grab my pencil and I traverse it from left to right, I see that my pencil would only cross the graph only once. So hence, this is a function. Now it's asking us for the inverse function. So opposite of a vertical line would be a horizontal line. So to find out if a graph has an inverse, we would perform what's called the horizontal line test. I would grab again my pencil or imaginary horizontal line. And if my horizontal line as I'm going from up down or down up, however you want to do it, if my pencil only crosses the graph only once, then this graph has an inverse. Okay, so again, to find if a function has an inverse, you perform this horizontal line test. Okay, all right. So let's determine whether the function has an inverse. F of x is equal to the square root of x minus 8, where x has to be greater than 8. And the only reason why they give us this other piece of information is that if x would be 8 or negative 8, oh, sorry, it has to be greater than 8 because if it was 8, then we would get 0. And if it would be less than 8, we would get negative numbers, which would we get errors. Okay, so to solve for this, we need to again perform our vertical line test so that we can graph it. Okay, so if we can't graph it, then what we can do is we can solve it algebraically. Let's find if this function has an inverse. And to do that, we first replace f of x with the variable that had been replaced with the f of x, which is y. Okay, so the first thing, I'll replace f of x with what it used to be as an equation, y, and then I'm going to interchange these variables. I'm going to make the x's become y's and the y's become x's. So let me go ahead and do that. So when I do that, I have this x equals the square root of y minus 8. Then all I have to do now is solve for y. So the first thing that I need to do is I need to square both sides. This is going to give me x squared is equal to y minus 8. I'm going to add 8 on both sides. So x squared plus 8 is equal to y. So this is the equation, but I need to indicate that what I just solved for was its inverse. So I need to replace that y value now with this symbol, f to the exponent -1. This means inverse. Okay, so again, this function here, its inverse would be x squared plus 8. Okay. All right, so let's look at this next example. It says, sketch the graph of the function by applying the leading coefficient test, finding the zeros of the polynomial, plotting sufficient solution points, and drawing a continuous curve through the points. Again, a polynomial graph is a smooth graph. Again, the way they taught us is that if we never lift a pencil or our graph does not have sharp turns, it's the graph of a function. That's what all this means. So we need to find its intercepts. We're going to use the leading coefficient to help us graph. Okay, so first let's apply the leading coefficient test. So the leading coefficient test says this: if my leading coefficient, which is the number associated with the degree of the polynomial. So in this particular example, my polynomial has a degree 2. The degree is the highest exponent number that variables have, right? So my highest exponent is a 2, so this is a degree 2. Okay, so being a degree 2, that means that this is an even function. If that exponent would have been an odd number, then this would have been an odd function. Okay, so this is an even function, and the leading coefficient of this degree function is a -1. So the rules state that if my leading coefficient is negative and my polynomial is an even function or an even polynomial, the graph is going to fall on the left and it's going to fall on the right. So let's look at the choices that they have here for us. So here, the answer is going to be the last one. The graph of the function falls on the left and falls on the right. Okay, so just to review just what I just said for all cases, again, this is to get you ready for your final. Okay, so the first two are examples of an even polynomial. Okay, so again, if your degree of your polynomial is an even number, then you are dealing with an even function. If the degree of the polynomial is an odd function, like for instance these two examples, which is a 3 is an odd number, so then these are odd functions. Our function is odd. Now the case that we just did here, if you see here, is this second one, right? The second one has the leading coefficient as a negative value, and it's an even function, so my graph is going to fall on the right and fall on the left. So just to quickly review, if my function was an even function and my leading coefficient was positive, it would rise on the right and rise on the left. Okay. If my graph was an odd function and the leading coefficient was positive, it would fall on the left and rise on the right. Okay. If my polynomial was an odd function, but my leading coefficient was negative, it's going to rise on the left and fall on the right. Okay. So again, in our particular example, our example was it falls on the left and falls on the right. Now it says find the real zeros of the polynomial. So what they're really asking us to do is find the x-intercepts. Okay, so we have a quadratic. There's several ways to find the x-intercepts in our quadratic that we have to do in our arsenal. We have the quadratic equation. We can factor. There's several things that we can do. So in this particular case, what we'll do is we will just factor it. Yes, I think this is my weapon of choice. I love to always factor if we can. So I know, and Ms. Chuka has a great advice for you guys too. And she says that if you can't factor it within 1 or 2 minutes, then don't just use the quadratic equation. The quadratic equation will always give you the solution, or will always result with the x-intercepts if they have any. Okay, so don't spend too much time trying to factor, but if you can factor it within the first 2 minutes, that's the way to go. All right, so the first thing I need to do is I set the quadratic equal to 0. And then I want to get rid of that negative. So I'm going to multiply a negative onto this equation on both sides. It's going to give me x squared minus 12x plus 32. This is a lot easier for me to do. So I need to find two numbers. I want to multiply them together, give me 32. And when I add them together, give me a negative 12. Well, what are these two numbers? A negative 8 and a negative 4. Negative 8 times a negative 4 gives me that positive 32, and negative 8 plus a negative 4 gives me the negative 12. So the x-intercepts for this equation is if x equals 8 and x equals 4. Okay, so there's are my intercepts. Now what I want to do is let me find more points. Let me find the y-intercept. To find the y-intercept, again, I have to set x equal to 0. So everywhere I see x, I'll plug in 0. And I get that y equals to negative 32. Okay, we have an equation to find the vertex. Or you could have completed the square also to find the vertex. But in this case, we're just using our formulas that we have learned. So to get the x value of the vertex, you have minus b over 2a. Once you have that value, you plug it back into the function and you're going to get the y value. Again, just to review on this function that they gave me, in standard form is ax squared plus bx. Okay, so in this case, my a is negative 1, my b is 12, and my c is negative 32. Okay, so again, here, my b is 12, my a is 1. So when I multiply this, I get my x value for the vertex is 6. Plug in that value back into the function. Everywhere you see x, you plug it in and you'll end up with 4. So the vertex of this parabola is 6, 4. So we have enough information now to graph. Okay, our vertex is here at this point, 6, 4. My x-intercepts is crossing the x-axis at 4 and 8. Again, we can't see it, but it's crossing the y-axis at negative 32. And then I knew that my behavior fall on the left and fall on the right because my leading coefficient test proved that since my leading coefficient was a negative number, it was going down. Okay, so these are all the points that we needed in order to graph this example. All right, so let's find solutions, let's find zeros, let's find roots of a polynomial. All these things mean the same thing. So in this particular one, f of x is equal to x cubed plus x squared minus 9x minus 9. Now, one of the things in order for us to, sometimes these polynomials are hard to factor or they're practically impossible to factor or find out what the zeros are. There's something that can help us find possible zeros, and that's called the rational zero test. In the rational zero test, to find the possible zeros of a polynomial is you'll get the factors of the constant term. Again, you don't have to worry about the sign, okay? The value of my constant term here is a 9. So the factors of 9 are 1, 3, and 9. Okay, then I get the factors of the leading coefficient. The leading coefficient is a positive 1, but again, I'm not interested whether these values are positive or negative, because if you see on my on formula, I'm gonna evaluate both parts, the positive and negative of these factors values. So again, the factors of my constant were 1, 3, and 9. So I'm gonna look at positive 1 and negative 1, positive 3 and negative 3, positive 9 and negative 1. And I only had one factor for my leading coefficient, which was 1. So I'm going to both look at both the positive one and the negative one. And then I would do these divisions. I would start with the positives. Positive 1 divided by the positive 1 would be 1. Positive 1 divided by a negative 1 would be a negative 1. Okay, so if I do this for all of these, I get this. These are the possible zeros: negative 9, 3, negative 3, negative 1, 1, 3, and 9. Again, this was a test. Like I like to joke with students, back in when we were in COVID, when we got tested, we always wanted that test to be negative. We never wanted it to be positive, right? But when we do this test, okay, it could be a negative result or a positive result. So it's just a test. It's not telling us that these are the zeros. So just to here, in this polynomial, since it's a degree 3, at most it's going to have 3 zeros, and it gave me 1, 2, 3, 4, 5, 6 possible zeros. Give me double of what I really have. Again, but it's a test. Okay, and you might be asked this on your final to find the possible zeros using the rational zero test. Okay, so if I actually really wanted to find a true zero, what I would do to practice is let's use synthetic division. Synthetic division is a way to divide the polynomial with our possible zeros. And if our remainder is 0, then that means that that value is an intercept, or that value is a 0 of the polynomial. Okay, so just to review also synthetic division, you got to make sure that your polynomial is in standard form, meaning the exponents are in decreasing order, which they are, 3, 2, 1 constant. You also got to be careful that you have placement value for all values. I have a 3, 2, 1, 0. If any of these values were missing, I would use 0, okay? But I do have them all. So all I'm going to do is grab the coefficients of each of these terms, have 1, 1, negative 9, negative 9. So I'm starting with the first choice on my rational zero test, which is 1. So in synthetic division, what I'll do is I'm going to bring down the 1 first, and then I'm going to multiply 1 times 1. 1 times 1 is 1, and I put it here on the second column, and then I add. 1 plus 1 is 2, and then I do the process again. 1 times 2 is 2, and then I'm going to add it with a negative 9. So negative 9 plus 2 is negative 7. Let's multiply 1 times negative 7. That gives me negative 7. So negative 9 plus a negative 7 is a negative 16. This last value is my remainder. And since my remainder was not 0, 1 is not a solution, 1 is not a 0, 1 is not a root. So let's go ahead and try it again. Let's go ahead and try negative 1. Again, the same process. I'm going to multiply, and when I do this, now I get a 0. This last value as a remainder makes us very, very happy, because what this tells us is that at x equals negative 1 is a 0, okay? Is a solution, or is an x-intercept of this graph. And the reason why I also want to do synthetic division, because if I wanted to find all the zeros of this polynomial, the quotient, meaning the remainder of this division, is a lot easier for us to factor. So if you notice, we started with a degree 3 polynomial, but when we do division, whether it's long division or synthetic division, we're always going to lose a degree of the polynomial. So here my quotient, if I write it as a polynomial, my quotient is x squared plus 0x minus 9. Okay, so if you see here, this is a lot easier for us to solve the remaining 2. Okay, I have 1, 0. Again, this polynomial should have at most 3 zeros. I already know one of them at x equals negative 1. And the other 2 is easy to see, easy to do by using our square root property. I'm going to add 9 on both sides. I'm going to take the square root of both sides. And I see that the square root of 9 is plus or minus 3. So hence, these are my 3 zeros. My 3 zeros are x equals negative 1, x equals negative 3, x equals 3. Okay, so if I wanted to graph my polynomial again, let me use the information that I used before. I'm going to use my leading coefficient test, and then I'm going to use some additional points to be able to graph this. Okay, so These are my x-intercepts at -3, at -1, at +3. Again, my polynomial is a degree 3, which is an odd function. So since it's odd, I'm going to look at a leading coefficient, which is a positive number. So then since this is an odd function and my leading coefficient is a positive value, this graph is going to fall on the left and rise on the right. So I put my arrows here. So things are going in between here. So this is where the additional points will come in handy. Okay, I want to pick values between -3 and -1 to see what's happening in the graph in here. And then I also want to pick values between -1 and 3 to see what happens. And this is why I picked these values. I picked -2, I picked 2, and I picked 1. Again, when I picked -2, the y value was a 5. When I picked +2, the y value was a -6. And when I picked 1, the y value was a -16. So if I would plot these additional points, again, I try to do a small, smooth curve, connect these dots, and voila. And here's my graph of my function. Yes. Okay. So let's move on to this new example. It says use the given zeros to find all the zeros of the function. So again, they give us another degree 3 polynomial. So hence, this function should have at most 3 zeros. But they gave us already 1 zero. They said that one of the zeros is 4 plus 2y. And again, this is to practice our complex numbers. This 4 plus 2y is a complex number because it has a real part with an imaginary part. The real part is 4 in red, and the imaginary part in black is the 2y. So here, let's go ahead and practice using complex numbers with synthetic division. Okay. So again, I'm going to bring down my 1. Oh, but first, let me double check. It's a degree 3. Do I have a placement value for all of them? And is it in the correct order? And the answer is yes. I have a 3, 2, 1 constant. They're in order, and I have a value for all of them. So let me grab the coefficients. I have 1, -12, 52, and -80. Let's go ahead and start. 4 plus 2i times 1 is just 4 plus 2i. Minus 12 plus 4 2i is just minus 8 plus 2i. Again, this guy did not have an imaginary value, so I just added the real parts. And again, this is the reason also why I want to do this problem, just to show you how, because you may be tested on adding and subtracting complex numbers, and the way you do that is just the real with real, imaginary with imaginary. This one did not have an imaginary part, so 0 plus 2i is just a 2i, but the real part is a minus 12 plus 4, gives me with a minus 8. I also like it because it also helps me practice multiplying complex numbers. Okay, so what I want to do is I want to multiply 4 plus 2i with a negative 8 plus 2i. And again, the way you do this is just like FOIL. It's just the distributing of the two terms, right? Or the binomial. The 4 times the negative 8 is a negative 32. The 4 times the 2i is the 8i. 2i times negative 8i is a negative 16i. And the 2i times the 2i is a positive 4i squared. Okay, just to review, the 4i squared becomes the I squared is a -1. So I multiply that times my positive 4, gives me the -4. And then I added the like terms here. Let me go back to this one. So you have two like terms. The 8i minus 16i gives me the -8i. And again, I know that I squared is the representation of the -1. So a -1 times a positive 4 gives me the -4, which leaves me with this polynomial. Excuse me, not polynomial. This expression. So I can still add like terms. It's not in standard form. I have a real part of -32 and a -4. So let me add those two together, and I have a -6 minus 8i. Now again, I'm adding real with real, imaginary with imaginary. There was a 0 for imaginary, so 0 minus 8i is still the -8i. But the real part, 52 minus 36, is 16. So let me go ahead and do the multiplication again, which is there. Again, combine my like terms and simplify. And I'm going to get this value, 64 plus 16, which is 80. Okay, so negative 80 plus 80 is 0. So the quotient on this one, again, I started with a degree 3. I lose a degree. So I start with the x squared, 1x squared. This negative 8 plus 2i refers to the x term. this 16 minus 8i is my constant term. Okay, so again, this is just a way to practice our complex numbers. Okay, all right, so if I really wanted to find all the zeros, because this is what they're telling me, what I can do is I can take the quotient and do the synthetic division again, okay, to simplify this, because this number, to get the zeros from this, it's a little bit complicated. So let me go ahead and do synthetic division again with the quotient. Okay, my first value is 1, my second value is a negative a plus 2i, and then my constant is a 16 minus 8i. Again, I'm gonna bring down my 1. 4 minus 2i times 1 is just 4 minus 2i. A negative 8 with a positive 4 is a negative 4. 2i minus 2i is 0. Just leave me with a negative 4. Let's multiply that again. So 4 times a negative 4 is a negative 16. Negative 2i times a negative 4 is a positive 8i. And then I get 0. So now you see that my quotient is just, I started with x squared. Now I lose a degree, so this is just x, and this is the constant term minus 4. So it's easy to solve for the x, which is 4, right? So one thing we know is that when they're giving us the complex number with imaginary, that came from a square root, right? That had a negative number, but square roots always have two numbers. So even though they just wrote one solution on there, I really have two. So and now I have my 3. So let me show you what I mean. Here, the zeros for this solution are x equals 4. Okay, so there's a typo here. This should be 4, not 0. Okay, and then I had the 4 plus 2i, but again, because they're the square root, there's always the plus or minus. So it's a 4 minus 2i. So these are my zeros again. This should be a 4, not a 0. Okay. All right, so let's move on to rational expressions. So this is a function which is in rational form. Rational form means I have a fraction. So I have a numerator and denominator. So the first thing that they ask us is state the domain of the function. So when we're dealing with fraction, excuse me, we never want the denominator to be equal to 0. And if our denominator, it can ever become 0, or there's a value that we can put in that's going to give us 0 on the bottom, then that's a restriction. We don't want to use that value, because then we would get an error. That's what happens when the denominator has a value of 0. Okay, it has an undefined function, or if you plug it into our calculator, 1 divided by 0, our calculator is going to tell us error, cannot do it. So again, if we don't see it, we would put the denominator equal to 0. We would set x plus 3 equal to 0. And then let me see if I have it. And yes, here we go. So x plus 3 equal to 0, and we would solve for x. So if we solve for x, we subtract 3 on both sides, and we see that if x would be a negative 3, we can see it here, minus 3 plus 3 would give us 0. So hence, this is the equation of also the value that we cannot use, which is going to restrict our domain. But this value also has importance, okay, which I'll talk about it right now. But again, if I were to answer what is the domain of this graph, would be all real numbers except this value, negative 3. So which is going to be our answer? Our answer would be this last one, right? All real numbers except when x is equal to negative 3. Okay, now this information here, well, I'll get to it. Let me go step by step. So the next thing that the problem wants us to do is to identify the intercepts. We'll start with the x-intercept. Again, we've done this already. So I'll zoom by through this. To find the x-intercept, I'm going to set y equal to 0. So everywhere I see f of x was replaced by y. So let me replace that with 0. And then I'm going to multiply x plus 3 on both sides. And when I do that, I get this statement, 0 is equal to 1, which is a false statement. So when I have a false statement, when this is not true, what this is telling me that this particular function is not crossing the x-axis. It has no x-intercepts, okay? Now, if I would have gotten a true statement, that value would have been the value of the x-intercept, okay? So let's get the y-intercept. To find the y-intercept, I'm going to set x equal to 0 and then solve for y. So here we see that by simplifying, we have our y-intercept is at 0 and 1/3. Okay. Now they want us to find the vertical and horizontal asymptotes. And this is what I had mentioned to you here. When I was trying to find the domain of this function and I found the restriction, that equation is basically the vertical asymptote. This is the value that I cannot use for x that will create an error on my graph. And that asymptote, when we're talking about asymptotes, are imaginary lines. Again, here at x equals 3, in our computer is as a dots, but on paper we talk about it. It's a dashed line, but here it's a dotted line on the computer. But at this vertical line, we cannot use 3 because if we would have used 3 again, it gives us an error on our equation. Okay, so our vertical asymptote for this particular problem is at x, sorry, -3. That graph is incorrect. That line should have been on the opposite side. So again, the vertical line of our asymptote is at x equals -3. Now, to find the horizontal asymptote, we have 3 different cases. Okay, so again, oh, this one is correct. The other one was just an example. Good. All right, starting to write. So here is -3 is my imaginary line represented as dots. Yes. But now to find my horizontal asymptote, there's 3 different cases. So the first case is this. If the degree of the numerator is less than the degree of the denominator, we always have a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, we have a ratio, or we have a fraction for our horizontal asymptote. And to get that fraction or ratio is we're going to grab the leading coefficient of the numerator divided by the leading coefficient of the denominator. And the last case, if the degree of the numerator is larger or bigger than the degree of the denominator, then there's no horizontal asymptote, but what we have is what's called a slant asymptote. Okay, so let's go ahead and look at the one that we have. So here, one way to write it is so you can better see it. Let me see here. We didn't have it here, but let me write it here for you. Here, let me write this fraction so you can better see it. X, how can I get 1 here? Anything to the 0 power is a value of 1. And then on the bottom, we have x plus 3. And if I see here, my exponent for my x is 1. So see here, the degree of the numerator is 0. It does have a degree, which is 0. The degree of the denominator is 1. So hence, the degree of the numerator is smaller than the degree of the denominator. So this guy has a horizontal asymptote at y equals 0. Okay, so again, it's represented as a dashed or dotted line here. All right, so let's move on. So now I have my asymptotes. I know that this graph is not crossing the x-axis, but I do know that it has a y-intercept. It had a y-intercept at 1/3. And we want to plot additional points to get a better graph of this rational function. So let's go ahead and look. So the points that I would pick would be points to the left of the -3, points between -3 and 0, and points to the right of 0, right? So these are the points that I would choose. I would choose -2 and 2, -4 and -5. These are just more additional points to get a better idea of my graph. Okay, so when I solve these points for x and y, again, I would plot them, and then I would try to do a smooth curve for this graph, and I would see that, again, I let the computer do the work because it's much nicer, and this is what it creates, right? It creates this rational graph, okay? All right, I've got 6 minutes. So again, if you're doing stuff on the computer or you have an online class, these are hopefully these are easy. Once you know what you're looking at, you have a multiple choice. So again, the right answer on the computer for this graph that's a multiple choice is easy to see. It's this first one. This one, obviously, it has the wrong vertical asymptote, correct horizontal. This one has the incorrect vertical asymptote as well. This last one has the correct vertical asymptote, but it has the wrong direction of my y-intercept. You see that it has a y-intercept at the negative where it's supposed to be at the positive. Okay. All right. So let's go into logs. So on this particular one, I love to do this example because it's one that my students always see. Okay, so I have the log of base 5 with a division of square root of x squared minus 9 over 4. And the problem says use properties of logs to expand the expression as a sum and difference. Okay, so the first thing that I see inside this log, I have two things that are being divided. So then that is going to apply my quotient rule. And my quotient rule says that I would have the log of base 5 of the numerator, which is the square root of x squared minus 9, minus the log of base 5 of 4. Okay, then what I try to do is, do any of my values have exponents? And the answer would be yes. And if we have exponents, that means that we are going to be able to use our power rule. So the first one that I see is the square root. The square root can be written as an exponent, and the square root as an exponent is 1/2. Okay. Um, so here, now that I have an exponent, I can apply what's called my power rule. That says that when you have a log to an exponent, you're going to multiply that exponent to the log or move it to the front. Okay, so then I have this 1/2 log of base 5 of x squared minus 9 minus log of base 5 of 4. Okay, then what I'm going to do is I'm going to factor out this x squared minus 9. I see that x squared minus 9, this is a difference of squares. Okay, um, so that this x squared minus 9 is basically just x minus 3 times x plus 3. So if you see here, I have a product of two things that are being multiplied inside a common log of base 5. So now I'm going to apply the product rule. And my product rule says this, that when I have two things that are being multiplied inside the log, they can be expanded by addition. So I will rewrite this as 1/2 the log of base 5 of x minus 3 plus 1/2 the log of base 5 of x plus 3 minus the log of base 5 of 4. Okay? And that's it. That's my answer. Okay? All right, so let's condense. Let's do the opposite instead of expanding and condensing. And I think I have time to do just one more, and I'll just do the A. So let's do the solution for the A. I have a log. I have 3 logs. Now, in order for you to use the properties of logs, they all have to have the same base. If any of those have a different base, then my properties cannot be applied. They are only applied to logs that have the same base. Now, in this particular one, the base is given by the the subscript. Here, there's no number here. So when they don't write a number, we automatically know that this is a log of base 10. Okay, so when there's no base, the base is automatically base 10. So these all logs have the base 10. They're all the same. So I can apply my properties. So the first property that I'm going to apply is my product rule. That says that when I have a number being multiplied to a log, that is represented as an exponent. So I'll go ahead and do that. Log of base x minus the log of y to the 6 plus the log of z to the 7. Okay. Now, I have to follow order of operations, but since they're all addition and subtraction, the order really doesn't matter. But since this minus is in the front, we do have to create our own um, property. Yes, so here, the first thing that I will do is I'm going to combine the left and right sides. But again, notice the subtraction for the quotient rule. So here, the first thing that I'm going to do is I'm going to do the log of base x minus the log of y to the 6. When I have two logs that are being subtracted from each other, again, this is the quotient rule that says that I'll divide the first input, x divided by the other input of the log. So I have the log of base 10 of x divided by y to the 6. But then now I have two logs that are being added to each other. This is the product rule that says that I'm going to multiply the inputs together. So again, this is the log of base 10 of x divided by y to the 6 times z to the 7. To simplify this, to make this a little bit nicer, my final answer here is a log of base 10 of x times z to the 7 y over 6. Again, thank you all for joining us. Sorry for the little delay. I wish you the best of luck in your finals. This was our last Happy Math Hour for this session. Again, good luck to all of you. Thank you for joining me, and I'll pass it back to presenters. Thank you so much, and again, good luck.
Thank you, Mr. Carrizales, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on the YouTube playlist. Today's session will also be available on the playlist later on. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out the survey. We will be back in the summer with more additional TVE events. Today, just a reminder, today at 1 p.m. we will have a student success topic, which will be Hacking the Border by Dr. Servin. Again, thank you all for coming in. We hope that you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic. And I do want to wish everybody here in the room good luck with your finals, guys. And have a good day, man.